Okay, let's take a look at today's problem, trapping rainwater. We are giving an integer array. The array represents a histogram for a size width 1 bars. For example, this particular array, index 0, the bar has height 1, this bar has height 4, this bar has height 0, this bar has height 1. And after a rain, the water could be trapped in those valleys. And this problem asking for how much water this histogram can hold. For this particular problem, the water capacity is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 is the answer. How can we find the solution? The brute force solution is we can scan from left to right. At each bar, we can see the longest bar at its left side is 0. So this place will not hold any water. For this position, the left side and right side both is lower, so this position won't hold any water. For this position, the longest bar at the left side has capacity 4, has height 4. The longest bar at the right side has height 3. So the water at this position has depth 3 minus 0. So this is how much water is held at this position. For this bar, the same limitation applies. So the water capacity at this position is 3 minus 1. The same apply here as well. The longest bar at the left side is this one. The longest bar at the right side is this one. So this one decides the capacity. So 2 minus 1, this is how much water is held here. As we can see, for this approach, we just have to find the shorter limitation at the left side and right side, and we can use the height to calculate the capacity at this position. The time complexity is n squared because for each position we need to search left in order to find the longest bar, and then we search right in order to find the longest bar, and the shorter bar decides the water capacity. We have n positions. Each position we search n positions, so totally we get n squared time complexity. The space complexity is O1. And in order to find the longest bar at left and right, we don't have to search for each position. We can use dynamic programming. If at this position, for example, we know the longest bar is here, then for this position, we don't have to search the left side anymore because the left side we already know the longest bar. The only thing we need to worry about is if the current position has a bar taller than the longest bar at the left side, then we can make the decision. For this one, the same thing applies. We just have to compare this height with the longest bar at the left side, and then we immediately know the longest bar at the left side. So in order to know for the longest bar on the left side, we just have to scan once. Then we calculate it for each position, the longest bar at the left. Then we iterate another round. This time we start from the right side, and we calculate the longest bar at each position on the right. Then we iterate the third time. At the third time, we already know at each position what is the longest bar at the left and the longest bar at the right. Then we can find the shorter one. Then use that to calculate the capacity at each position. This approach have time complexity On. the space complexity is O(n) as well, because this time we needed 2 extra arrays to store the longest bar at the left side and the longest bar at the right side for each position. There could have a better solution. We can use 2 pointers, say. The left pointer point at the left edge, the right pointer point at the right edge initially, and those 2 bars form a water container which can hold water. And the shorter edge is a bottleneck, and we start move inward from the bottleneck. Say, since this time the 2 sides is the same height, we move inward from the left. We move then we examine this bar. This bar is taller than the left edge, so we just find a new left edge, and this bar and this bar form a new water container, and the bottleneck is at the right side, so we search from the right side instead. In the next position, this bar is shorter than the bottleneck, so this place can hold water, and the water capacity is 1 minus 0. Next, we search inward from the bottleneck side. At this position, the bar is taller than the bottleneck, so the right side edge is updated with this bar. So this bar and this bar now became a new water container. Again, we search from the bottleneck side. We move inward, consider this bar. It is shorter than the bottleneck, so we know the water capacity is this height minus this height, which is 1. Then we move inward. At this position, this bar is taller than the bottleneck, so we just update the right edge. Now this one and this one form a new water container. Again, we search at the bottleneck side. We move inward. This position is shorter than the bottleneck, and the water capacity is this one. Then we move inward. At this position, the water capacity is this one. Then we move inward. Here, the water capacity is this one. Then we move inward. Now the left side, right side just meet. And we finished our searching. During the process, we just calculated the water capacity. The time complexity is O(n). We didn't use any extra array to store anything, so the time complexity is O(n), the space complexity is O(1). Let's take a look at the code. This is our water capacity. First, our left boundary and the right boundary is set as the start position and the end position. And we have 2 extra pointers to examine. The next bar has the left side and right side. As long as those 2 pointers not meet, we search at the bottleneck side. Say if the left side is the bottleneck, then we just see if the neighbor is shorter than the bottleneck. If yes, we add the capacity to the total capacity, and we search inward. If the neighbor is taller than the bottleneck, then we just update the bottleneck. Then we go ahead and recalculate the bottleneck. In the case the right side is the bottleneck, then we search from the bottleneck side, from the right side. In order to search the right side, if the neighbor is shorter than the bottleneck, we just add the capacity into the total capacity. Then we search inward. If the neighbor is taller than the bottleneck, we just update the bottleneck. And we go back to the while loop again. We recalculate the bottleneck side, and we search inward. At the end, the 2 sides across and we just get the total water capacity. The the space complexity is a 1. So this is the advantage of this approach.